Okay, we're talking physical chemistry, chapter 12, section 6 now. We're going to talk about two-component equilibrium at the liquid of a liquid and vapor. Now remember, for two components, we have the number of independent components is equal to 2. Now we have this formula, the degrees of freedom is equal to the number of independent components minus the number of phases plus 2. So since we have 2 for the number of components, we have 4 minus the number of phases for the degrees of freedom. Now, if the number of phases is equal to 1, then the degrees of freedom is equal to 3. That would be temperature, pressure, and mole fraction. Now, if we wanted to graph that, though, that would have to be a three-dimensional plot, and those can be difficult to understand. So what we're going to do is we're going to keep temperature or pressure constant, and then we'll make a two-dimensional plot. We'll just keep one of those variables fixed. Now let's say we have an ideal solution at fixed temperature. Okay, remember T is temperature, of course. So let's say we have two liquids. I'm going to call them A and B, and they're both volatile. Remember, volatile means they can evaporate, so they have a vapor pressure. So the T is constant, we just said that, and it's greater than the temperature of freezing. So we've got no solid, just liquid and gas. So we're going to have the mole fraction of A is the number of moles of the substance A total, and divided by the total number of moles. And we're talking about a closed system, of course. So this is the total overall mole fraction of A in both phases, the liquid and the gas phase, vapor phase. Now, likewise, some of that A is in the vapor phase, some of that is in the liquid phase. So the mole fraction of A could also be written as the number of moles of A in the vapor phase plus the number of moles of A in the liquid phase. So we're using this subscript V for vapor and subscript L for liquid. So then, of course, the number of moles total would be the number of moles of A in the liquid phase plus the number of moles of A in the vapor phase plus the number of moles of B in the liquid phase plus the number of moles of B in the vapor phase. Now, here's a graph. What's going to happen if we increase pressure? So we have our substance A and B. We've got a constant temperature bath. We're going to apply a pressure down on A and B. So we're going to push this piston down. That's going to increase the pressure. Or we could raise the piston and that'll decrease the pressure. Now we're going to start with just pure A and B, liquid, no gas, no vapor. What we're going to do is we're going to raise the piston to decrease the pressure. Now we're going to build a phase diagram here. We're going to have the mole fraction of A, three different mole fractions of A. So we'll call it just triple prime, double prime, and single prime. And we're going to have increasing pressure on the graph. So like we said, we're going to start at this higher pressure and decrease the pressure going down. So this C is our starting point. As we decrease the pressure, we're going to call D, where we just start to get vapor. And then we're going to call this point F, where there's no more liquid. All the liquid is vaporized, and all we have is the vapor phase. So we're going to start at C prime. We're going to decrease the pressure. Then D prime is when vapor first appears. Now below D prime, remember that's pressure, lower pressure, that is when the vapor of both substances with more than one of the, if you have two substances and one is more volatile than the other, then you're going to have more of the volatile one in the gas phase and less of that in the liquid phase. But then at F prime, like I said, that's going to be where there's going to be no more liquid. That's going to be the end of the liquid. And then so below F prime, everything in our container is vapor, no more liquid. So at C prime, the mole fraction of A is equal to the mole fraction of A in the liquid. At D prime, the mole fraction of A is still roughly equal to the mole fraction of A in the liquid, because there's only just a tiny bit of vapor. It's very close to equal. This wiggly equal sign means roughly equal to. Now let's say we have the mole fraction of A in the vapor phase is equal to the mole fraction of A in the liquid phase times the pressure of A in the pure state divided by the total pressure. That's Rolle's law. And remember, just P is total pressure for all substances. And then 2, we have the mole fraction of B in the vapor phase, and that's equal to the mole fraction of B in the liquid phase times the pressure of pure B divided by the total pressure. Now, we're going to divide 1 by 2. We can do that because obviously none is 0. So we're going to divide this by that, and this by that. So if PA star is greater than PB star, then the mole fraction of A in the vapor phase is going to be greater than the mole fraction of B in the vapor phase. So what we need to know is, what is this mathematical function that will describe the points, like D prime, D double prime, D triple prime, or F prime, F double prime, and F triple prime? Well, we know that the total pressure is equal to the partial pressure of A plus the partial pressure of B. And using that formula above, Raoult's law, we could say, okay, then that's equal to the mole fraction of A in the liquid phase times the pressure of pure A plus the mole fraction of B in the liquid phase times the partial pressure of B. That's assuming 2 components, obviously. Well, and likewise, the mole fraction of A plus the mole fraction of B has to be equal to 1. And that's, again, because we only have 2 components. Then we have the pressure is going to be equal to the mole fraction of liquid phase times the pressure of A in the pure state plus 1 minus the mole fraction of A in the liquid phase times the pressure of B in the pure B. That's why we did that XA is equal to 1 minus XB and substituted it in. So then we get just simplifying, doing some distribution, we get the pressure is equal to the mole fraction of A in the liquid phase times the pressure of pure A minus the mole fraction of A in the liquid phase times the pure pressure of B plus pure B, the pressure of pure B. So now we want to combine this mole fraction of A in the liquid phase. So we get the pressure is equal to the pressure of pure A minus the pressure of pure B times the mole fraction of A in the liquid phase plus the pressure of B in pure B. Now, the reason we wrote this like this is because we have a straight line. It's in slope y-intercept form. This will find our D points. Oops. Now, like I just said, that equation is linear. It's a line. So we have the mole fraction of A in the liquid phase is roughly equal to the mole fraction of A at D prime, since we're just starting to vaporize it yet. Pretty much everything is still in the liquid phase. It's the first droplet. So here's increasing pressure, starting with mole fraction of A 0, going up to pure A. So we have PB star, D prime, D double prime, D prime, PB star. So if we have the mole fraction of A is 1, you have pure A. If you have mole fraction of A is 0, then you have pure B. Now this graph is written assuming that the pressure of pure A is greater than the pressure of pure B. Now let's say we substitute for the mole fraction of A in the liquid phase using this formula here. The mole fraction of A in the vapor phase is equal to the mole fraction of A in the liquid phase times the pressure of pure A divided by the total pressure. Well, then what we get is the mole fraction of A in the liquid phase is equal to the mole fraction of A in the vapor phase divided by the pressure of pure A divided by the total pressure. Now, we have, substituting that back into our straight line, we get the pressure is equal to the pressure of pure A minus the pressure of pure B times the mole fraction of A in the vapor phase divided by the pressure of pure A divided by P plus BB star. Now, here's the problem. We have P in 2 different places. Oh no, wait, is that a row? Ha! Okay, I was calling that, I made a mistake. No, that's right, that is P. Okay, never mind, my P looks like a row, sorry. So we need to solve for P. And what we get is that the P is equal to PA star times PB star divided by PB star minus PA star times the mole fraction Chi A V plus PA star. Now the problem with this here, solving for P like this, is not a straight line. Now these are for our F points. Now this is what it looks like here. So we have the pressure against mole fraction of A. So we have pure B over here, pure A over here. And again, this is assuming that the pressure of pure A is greater than the pressure of B, so that's why it's sloping up. So again, we have our D points as a straight line. I didn't draw it very well, but F is always increasing. It is positive, just it's not a straight line. Now let's talk about ideal solutions. We're going to talk about the lever rule and the tie lines. So we have this diagram we just drew before where we have pressure against mole fraction of A. So we have pure B, pure A. Now remember, this is the overall mole fraction of A in the entire system, vapor phase and the liquid phase. And again, we're holding temperature constant, so we don't need a three-dimensional graph. Now if we are somewhere in this area, we can pick a point, looks like I called it E. We can draw a horizontal line all the way to this curve and this curve. This horizontal line is called a tie line. So where it intercepts here, so this is the CD and E we talked about before on the previous charts. So we're calling this point here H and this point here I. Now isopleth means constant composition. So that's this vertical line, because at any point we've got constant concentration of A. So that's the vertical line, and the horizontal line is the tie line. So remember, Na is the number of moles of substance A in the liquid and vapor phase. Nl is the total number of moles of A and B in the liquid phase. And then Nv would be the total number of moles of A and B in the vapor phase. Now we already said Chi A, the mole fraction of A, is equal to the number of moles of A divided by the number of moles in the liquid and the vapor phase. And then the number of moles of A is equal to the mole fraction of A times the number of moles in the liquid phase plus the mole fraction of A times the number of moles in the vapor phase. And then we get the number of moles of A is equal to the number of moles of A in the liquid phase plus the number of moles of A in the vapor phase. I think we established that before. And then the number of moles of A is going to equal the mole fraction of A in the liquid phase times the number of moles in the liquid phase plus the mole fraction of A in the vapor phase times the number of moles in the vapor phase. Now we have the mole fraction of A times the number of moles of L. I'm just setting those two equal to each other. So we get the mole fraction of A times the number of moles in the liquid phase plus the mole fraction of A times the number of moles in the vapor phase plus the mole fraction of A in the liquid phase times the number of moles in the liquid phase plus the mole fraction of A in the vapor phase times the number of moles in the vapor phase. And let's see here. I move these to I move the liquids to this side, the vapors to this side. So we get the mole fraction of A times the number of moles of liquid minus the mole fraction of A in liquid times the number of moles in liquid is equal to the mole fraction of A in the vapor phase times the number of moles in the vapor phase minus the mole fraction of A in the total minus times the number of moles in the vapor phase. So we're going to factor out the number of moles. So we get the number of moles in the liquid phase times this whole quantity, mole fraction A minus the mole fraction of A in the liquid phase. And that's equal to the number of moles in the vapor phase times this whole quantity, the mole fraction A in the vapor phase minus the mole fraction of A. Now, let's see, where was I? So the mole fraction of A, if we're talking about this line up here, this mole fraction of here, we're at XA prime. So this XA, we're at XA prime right now. So draw in a line segment. This is a mathematical notation. I don't know if we normally do it in science. But so we have the number of moles. Okay, so this is length. If I show EH, this is the length of line EH. So the number of moles in the liquid phase times that EH, the length from E to H, is equal to the number of moles in the vapor phase times that length EI. This is called the lever rule because it works kind of like a teeter-totter or a lever. So remember, this length EI and EH, those come from the graph that I was showing you just now. So here we are, the lever rule. The number of moles in phase alpha times, or no, substance alpha. Oh yeah, this will work for phases too. So the number of moles in phase alpha times the length of, the length of the line in that phase alpha is equal to the number of moles in beta times the length of beta. So that's the lever rule as it applies to phases alpha and beta. So like I said, in this case, this L means length. It's not a subscript for liquid, obviously. And then N would be the total number of moles in the phase. We can also do this in weight fractions, where we have like M is the weight fraction of alpha times the length of alpha, and that's going to be equal to the mole fraction, or weight fraction, sorry, in the beta phase times the length in the beta phase. Now that top curve is also what we call the bubble point line, because that's where we first start seeing bubbles form from the liquid. Now we're going to talk about, we've just been talking about constant temperature. Now we're going to talk about an ideal solution at fixed pressure. So P is equal to a constant. So now we can graph temperature versus mole fraction of A. Notice it's the same sort of thing. We have 0 over here, so we have pure B. And then we have 1 over here, so that's pure A. So notice it's the reverse. If A was A is a lower temperature here than that. So this is again assuming constant P, and we're still assuming that A is more volatile than B. Since it had higher pressure, it's going to have lower temperature. So the mole fraction of A2 is the composition of the vapor from the mole fraction of A1. So A3, so here's A1, A2, just so you know. So the mole fraction of A at whatever 0.3 is the composition of the vapor from mole fraction of A2, and so on. Okay, that wasn't written very well. So if we have like an XA, we'll get this XA1 and XA2, depending on how the line goes. So what that's saying is when you split it up, you'll get these two. So if you keep doing that, you can actually take advantage of this and separate the two substances. This is called distillation. Now remember, if it's got a lower vapor pressure, it's going to have a higher boiling point, and so on. And when you keep doing this distillation, that's called fractional distillation. So let's say we have a theoretical plate. So the maximum degree of enrichment for any one distillation step, each horizontal line in this graph is a theoretical plate. So if you start out here and you want to separate them by boiling or however wide this line is, that's the most you can separate them. So in real life, if you add more plates, you can get better separation. But if the boiling points of these two substances are close together, then you're going to need more theoretical plates to separate them. Now in real life, of course, a fractionating column can be actually many feet high and have thousands of theoretical plates. If we're talking about something like an oil refinery where they separate the diesel from the gasoline and so on. Now if we put beads in a fractionating column, or we can make the fractionating column zigzag, that'll increase the theoretical plates and help us separate the liquid from the vapor. Okay, now let's say we don't have an ideal solution. Now we've got a graph here that's educational because it's wrong. It doesn't make any sense. Now let's say we've got constant temperature, and we're going to do pressure versus mole fraction, just like we've been doing. So we have pure B here and pure A over here. And let's say that somehow they curve up like this. So we have at higher pressure we have the liquid, lower pressure we have the vapor, and then in between we have the liquid phase and the vapor phase. It seems reasonable. But let's say we have a point D up here. Well, the problem is we need to be able to make a tie line, right? A horizontal line to figure out, okay, if we're boiling off here, we're decreasing the pressure, we're just boiling some off, what's the composition going to be? See, if we try to draw a tie line, it's going to end up liquid, both sides of the tie line. That doesn't make any sense. So, based on a diagram like that, we can't determine what the vapor pressure is going to be from that diagram, because there's no horizontal. Oh, no, wait. Well, same thing with E. We won't be able to figure out the horizontal line, the tie line for E either, so we won't be able to figure out the vapor pressure for that. So this is what's going to happen. If we move that point D, or E, up to D, now look at what we've got here. So we've got our liquid phase up here, we've got our vapor phase up here, we've still got a liquid and vapor phase, and we've got another liquid and vapor phase. Now again, we're still assuming constant temperature, and the way we moved it up, we're calling this positive deviation. So this top curve here, this is called the liquid curve. The bottom curve, this is called the vapor curve. Now if we graph temperature versus mole fraction of A in the same scenario, so except of course we're assuming pressure is constant. So we've got our vapor phase up here at high temperature, the liquid phase down here, and what we've done is we squeeze these together. So we have a liquid and vapor phase here and a liquid vapor phase here. Now you notice there is one point where you go straight from liquid to vapor. You don't have any separate liquid and vapor phase. Then this point here, this mole fraction, this is called an azeotropic mixture. Now, if we have higher vapor pressure, remember we're going to have lower boiling point. So an azeotrope, this is a constant boiling mixtures. Because remember up here on the graph, you're boiling anywhere inside of here. But for this one azeotropic mole fraction, it only has one boiling temperature. Now, an example you've probably already heard of is about 96% ethanol and 4% water. So that's why a distillery or whatever making vodka or whatever, I guess, you can't get 200 proof alcohol just by distilling a water alcohol mixture. It won't work. You can't get them separate. Now you can't, so using distillation, you can't purify beyond the bottom point, the azeotropic mixture. Now if the mole fraction of A starts out greater than mole fraction of A prime, then fractional distillation is going to give you pure A and the azeotrope. If the mole fraction of A is less than mole fraction of A prime, then fractional distillation is going to give you pure B and the azeotrope. But here's the good news. If you change the pressure, it'll change the ratio for the azeotrope. So you can just change the pressure if you want to move that around. That is all for Chapter 12, Section 6.